All right, this is QQT problem number 1 from AP Classrooms, and this is going to be the solutions video. So problem 1 is definitely a energy conservation work energy theorem type of idea. So we have a block initially at position x equals 0 in contact with an uncompressed spring of negligible mass. The block is pushed back along a frictionless surface from 0 to x equals negative d, as shown above, compressing the spring by amount of delta x equals d. Okay, so our change in spring length is d. The block is then released at x equals 0, and the block enters a rough part of the track and eventually comes to rest at a position x equals d. Coefficient of kinetic friction between the block and rough track is mu. Now there's actually an error in this problem. This should actually read that it comes to rest at 3D. If you look at the picture, that's where it is. And if you look at the next couple of questions, they all refer to 3D. Now I was giving credit to people who had drawn the graph based on D and answered the question based on D instead of 3D. So I was kind of accepting two answers. So on the axes below, we need to sketch and label the graphs of the following two quantities as a function of their position between negative d and 3d. You don't need to calculate values for vertical axes, but the same vertical scale should be used for both. All right, so we need to look at the kinetic energy of the block and the potential energy of the block. Okay, well, at x equals 0, the block is released from the spring. So that means from 0 to 3D, we have no spring potential energy. So I'm going to draw that as a nice horizontal line for potential energy. Okay. So this is US down here. All right. So let's continue with spring potential energy because that's actually the easier one to graph from 0 to negative D. So spring potential energy, US or PES as it's written, is 1/2 K x squared, which means that spring potential energy is related to position squared. So if I'm graphing the energy versus the position, I should see some sort of curve. Okay, so when we are at negative D, here we have all spring potential energy, and we have to decrease to 0 by the time we get to x equals 0. Okay, so I'm going to draw a nice parabolic curve like that. Okay, now energy is conserved, which means any loss of spring potential energy has to correspond to a gain in kinetic energy. So my kinetic energy graph is actually going to look something like that, where I start at 0, and at this x equals 0 position, I have all kinetic energy. Okay, so this is my KE graph up top here. Okay. Now the block slows to a rest and eventually comes to a stop at 3D. Okay. So now we need to figure out what the graph should look like for the kinetic energy between 0 and 3D. Okay. So the reason why there is a change in energy, change in kinetic energy, is because work is being done. Specifically, work is being done by the force of friction. Okay. Now again, since I'm graphing energy versus change in position or energy versus position, I want to look at the relationship between kinetic energy and distance. And if I look based on the work equation, that change in kinetic energy is directly related to distance, which means I should see a nice line graph for kinetic energy between 0 and 3D. Okay. So that would get me full credit. And just to verify that, our scoring guide down here is I get 1 point for sketching either energy curve with reasonably correct shape, so energy curve, with a 0 and maximum values. So I have that. So that's talking about this part here. And for sketching two curves with shapes and values such that total energy is constant, even if the curves are incorrect. So I did that as well. I get 1 point for sketching potential energy is 0, and 1 point for sketching kinetic energy as a linear function from 0 to 3D. So I get all 4 of those points. Now in this year's AP exam, instead of actually drawing that graph, you might be asked to analyze the graph and say what's correct or what's incorrect. Okay, so now the spring is compressed twice as much. So instead of a delta x of D, we are now doubling that spring compression. A student is asked to predict what the final position of the block will be, whether the final position of the block will be twice as far. So they're thinking, if we compress the spring twice as much, will it take twice as far to slow down? The student reasons that since the spring is compressed twice as much as before, the block will have more energy. I like that part. Increasing the compression is definitely going to increase the energy, okay? Because spring potential energy is related to x squared. So if we increase x, PES is also going to increase. It's not an inverse relationship. So it will slide farther along. Well, that's for sure. It's going to slide farther along, but it's not going to stop at 6D, okay? Because with this parabolic or a quadratic relationship we see here, if we double x, then that's going to lead to 4 times the spring potential energy. And if we have 4 times the spring potential energy, then that means we have 4 times the kinetic energy, okay? Because all of that spring potential energy converts to kinetic energy. If we have 4 times the kinetic energy, then that means if the force of friction is staying the same, which it would in this case, we need to have 4 times the distance. Okay, so which aspects of student 1's reasoning are correct? So the student is correct that there will be more energy and that the block will slide farther. There is more energy in the system because spring potential energy and x have a squared relationship. As x increases, spring potential energy increases. More energy means more work must be done. So distance must increase. Okay. And then B2, which is incorrect. Okay. So the student is incorrect that doubling delta x will lead to a distance of 60. Really, doubling delta x leads to 4 times as much energy and 4 times as much distance. Okay. So then we need to use quantitative reasoning. So equations as needed to develop an expression for the new final position. Okay. Now, what a lot of people were doing is they were going right to 4 times 3D equals 12D. But that doesn't really show anything. Okay, it doesn't show that you know why these things are connected. So the first thing we would want to do is say that spring potential energy is 1/2 kx squared. Okay, so if we double x, then we get 4 times the spring potential energy. Okay, then we can say something like energy is conserved and PES max equals KE max. So we're going to get 4 times as much kinetic energy. Okay. Then we're going to work into the work energy theorem. Delta KE equals work, which in this case is going to be the force of friction times distance. Okay. Remember, the force of friction is going to be the same for both So if for KE, then for D, so 4 times 3D equals 12D. Okay, so we need to show our entire thought process. We can't go right to here. Okay, and just to show that, I'm going to go to the scoring guideline for that problem. Okay, so for part B, we get 1 point for identifying that the student correct is have more energy. I did that. I also said that traveled more distance, but that's okay. And then for B2, I get a point for saying that the student's incorrect, that the final position doesn't scale linearly. So I went the other way. I said that final distance is a squared relationship instead of is not linear. So I still get that point. Okay. Now for C. Okay, so C, we get 1 point for indicating that the final energy of the spring is 4 times as much. So I did that. For indicating that the frictional force is the same, I did that. For equating the initial energy of the spring to an expression that shows that the energy dissipated by friction is proportional to the distance the block slides. So that's what I did, or was attempting to do, when I was talking about this here. I was showing the connection between this spring potential energy and this final distance here. So they actually go through and show all of the different equations. So they said this here. Okay, so they wrote it more out in equations than I did. Okay, but they show that this force of friction is the same. Remember, force of friction is mu times the normal force, and for an object on a horizontal surface, the normal force equals Fg or mg, so that's where that mu mg is coming from. Okay, so they're saying that the work done, okay, we have the same force of friction, okay, so the work done in one has to equal u1, or essentially the energy in u1. Same thing here. So if we get 4 times the potential energy, then we have to do 4 times the work. The only way to do that is to do 4 times the distance, which they get 12D. Okay, so that's, in my opinion, slightly more complicated, but still gets the point across. And I like words more than equations. All right, let's finish out this problem. So in D, I need to explain how any correct aspects of students' reasoning identified in part B are expressed in my relationship, and explain how the incorrect aspects are done. So essentially I have to reference my equations in C and say how they match with my answers in B. Okay, so as shown in C, there will be 4 times or more energy in the system as the student predicted, because US and X have a square relationship. If you feel like you're saying the same thing like 3 times in this problem, it's kind of because you are. All right. C also shows that this square relationship translates to the distance traveled as well, showing the student was incorrect in assuming the block would travel twice as far. Okay, so I referenced what's correct, that there is more energy, and I've shown, and I referenced how C says that, and then I've referenced what's incorrect, that the student is saying it hasn't traveled twice as far, and I'm saying in C, we show that that square relationship transfers through to that distance. So let's go ahead and see what the scoring guide says. All right. So D says for indicating that the student is correct that the block has more energy expressed by calculations than the initial energy of the spring. So we talked about that. I get 1 point for indicating that the student's correct reasoning that the block will slide farther is expressed by the equation that indicates the work done by friction to stop the block. So I essentially say this by saying that we're going to travel farther in general. And for indicating that the student's incorrect, that there isn't a direct relationship between that compression length and the distance traveled, but rather it's a squared. So I talked about that. Again, you're almost saying the same thing 3 times through. On this year's AP exam, this is not going to be this case. Almost every single justify question will be a little bit different. If anything, you might be presented with these equations and asked to show how they agree or disagree with what the student is saying. That's likely something you would see on this year's exam. Okay. So that's it for this qualitative translation problem, number 1. See you soon.